Assalamualaikum warahmatullahi wabarakatuh. We are from Group 9 and we will present about ceramics, the material, structures and processing today. These are our contents, which consists of first, the ceramic materials, second, ceramic and glass structure, third, silicates and carbon form structures, and last, the ceramics processing. Hi, my name is Zunur Alwadi binti Ahmad Zaki. My matric number is 1202527 and I will present the ceramic materials, which consists of raw materials and properties of ceramic and silica glass. So first, let's recap last week's presentation where they have explained the meaning of ceramics, which is ceramics are made up of mixtures of clay, earthen elements, powders and water, shaped into desired forms, and then they are fired in a high temperature oven known as a kiln. So ceramic will be shaped and then fired to produce ceramic materials. And then ceramics are inorganic, non-metallic, and is a crystalline materials. As you can see the picture on the right side, they are the structure of crystalline and amorphous materials, where the amorphous structure has space between the atoms and it has irregular arrangement, while the crystalline structure has regular arrangement. Next is the integration of Nakli and Akli. As we know, Allah made humans out of soil or clay, and Allah said in the Al-Quran, وَلَقَدْ خَلَقْنَا الْإِنسَانَ مِنْ صَلْصَالٍ مِنْ حَمَإٍ مَسْنُونٍ, which means, and we did certainly create man out of clay from an altered black mud. Surah Al-Hijj verse 26. The word salsalin, which is clay, means human made out of dried clay, and then the word hamain is a black mud, which means it is a mud which it will includes water H2O in the process, and then masnoon, which means altered, which is clay has been molded into a shape. So as we can see here, the process is like the process of making pottery or ceramic. This means Allah already stated the process of making pottery in the Al-Quran, because from Surah Ar-Rahman verse 14, Allah said that humans are created from clay like pottery. And we can see here that the process includes H2O, which is water in the process to make the structure. And we know that human has very good structure, like manusia adalah sebaik-baik kejadian. So we use the same process in the making of pottery or ceramic, which is we use water to make a very good structure that gives great properties of ceramics that we will look after this. Next, we will look at the raw materials of ceramics. So ceramics are crystalline and they are formed between metallic and non-metallic elements. For example, they are formed from aluminium and oxygen, which is the alumina, Al2O3, or silicon and nitrogen, silicon nitride, and silicon and carbon, silicon carbide. So let's look at the division for ceramics and glass. The basic components for ceramics are clay, silica from quartz, and feldspar. The traditional ceramics usually contain the basic components and other substance. But modern ceramics nowadays that have been used in the industry and buildings and others, they contain oxides or non-oxides or combination of them. So the example of oxides are alumina or zirconia, and the example of non-oxides are carbides, borides, nitrides and silicides. Next, if we look at the glass are non-metallic and they are inorganic but amorphous. So they have the amorphous structure like I have shown the picture earlier, and some of the glass are classified as ceramic. So if we refer to the periodic table, ceramic are made from combination of one or more non-metallic elements in the dark blue region with the one or more metallic elements from the light blue region. So for example, the compound are like aluminum oxide, which is the alumina, boron carbide, silicon carbide, and tungsten carbide, which is used in forming ceramic materials. Each raw material contributes a certain property such as dry strength, plasticity, shrinkage, and others to the ceramic body, which gives the different properties to the ceramic materials to make different ceramic products. Next, we will look at the properties of ceramics. So, ceramic has low electrical and thermal conductivity, which means they are good insulators. And then they are resistant to high temperatures and harsh environments than metals or other polymers. And then ceramic has great hardness and strength, but they are very brittle, which is rapuh. And then ceramic has high compression resistance, and they also chemical inert, which means they are chemically unreactive. They will not react with other substances chemically. And then ceramic has high durability, which means they are long lasting and hard wearing. So why do ceramic has these properties? This is because these properties are related to the certain types of chemical bonding and the crystal structures in the ceramic material, because as we know that ceramic is crystalline material. So the good structure has made ceramic has these great properties. Next, we will look at the silica glass, which is the most common glass, and it can be said that silica glass is part of ceramic because it is made from silica, SiO2. So silica glass is a dense form of amorphous silica, SiO2, but it is still amorphous. And then it largely consists of silicon dioxide. It is different from pure silica glass, the fused silica, because silica glass contains some additional substances or impurities such as soda, Na2O, alumina, Al2O3, or phosphorus pentoxide, and others. Silica glass are made from combination of non-crystalline silicate with the combination of oxides. Because the non-crystalline structure of silica glass, it will have the charge imbalance. So the charge imbalance will be corrected by the counter cations such as Na+, because silica glass has the impurities and additional substances. Next, silica glass has various types depending on the composition of compounds in the ingredients. So some of the types of silica glass are soda lime glasses, borosilicate glass, phospholicate glass, and others. For example, the borosilicate glass is the Pyrex glass that we use in the lab. Pyrex glass has better temperature stability and it is less brittle than sodium glass. Now, let's look at the type of silica glass and their composition. So, for example, the soda lime glasses that I have highlighted. Soda lime has the composition of SiO2 silica of 74 weight percentage and 16 weight percentage of Na2O and others. The different composition of the substances will give the different characteristic and application for the different types of silica glass. So the last part from me is the characteristic of silica glass. The properties of silica glass is it has moderate melting point, while different from ceramic that has large melting point. Silica glass has small toughness, ductility, high stiffness, and creep resistance, which means silica glass resists changes in shape when being acted by physical force. Silica glass is suitable with the high temperature and wear resistant application. They can be easily formed because of the amorphous structure, but different from ceramic that cannot form because they are consist of crystalline structure.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Najam Timuddin. I'm going to continue with ceramic structure, which can be divided into four: ceramic, glass, silicates, and carbon. For ceramic structure, the structure called as oxide structure, A class structure. It It is called as oxide structure because containing oxygen and other metal oxygen and ions larger than metal cations. For the example, magnesium oxide, aluminium oxide, and cerium oxide. Close-packed oxygen in a lattice, usually FCC. Cations fit into interstitial sites among oxygen ions. There are two factors that determine crystal structure, which is the first factor is relative size of ions. Formation for stable structure. Based on the picture, we can see that smaller positive ion compared to the size negative ion will produce unstable structures. Size positive ion needs to be balanced with the size of negative ions to form stable structure. The second factor is maintenance of charge neutrality. Net charge in ceramic should be zero, reflected in chemical formula AXMP. Bond hybridization affects structure. Bond hybridization is possible when there is significant covalent bonding. It is defined as the mixing or overlap of the electron clouds from different orbitals, causing new hybrid orbital. Hybrid electron orbitals form when there is directional bonding, which is covalent bond. For the example, SiC, which is XSI is 1.8 and Xc is 2.5. The first structure for crystal structure is AX crystal structure, rock salt structure. The example for this structure is NaCl, sodium chloride. Same concepts can be applied to ionic solids in general. Cations, sodium, prefer octahedral sites. The second crystal structure is AX crystal structure, CsCl structure, calcium chloride. AX type crystal structure include sodium chloride, calcium chloride, and zinc chloride. Calcium chloride crystallizes in primitive cubic lattice, meaning the cubic unit cell has no nodes except at the corners. CsCl is made up of two interpolating cubes of Cs plus and other Cl minus. The ions are in contact with one another. The anion and cation would repel each other if they touch. Calcium chloride is more stable than sodium chloride because it forms a more stable crystal and releases more energy. The third crystal structure is AX2 crystal structures. Example for this structure are calcium chloride, CaF2, UO2, THO2, ZrO2, and CeO2. Cations in cubic sites. Antifluoride structure, position of cation and anions reverse. The calcium cation have formed a FCC array, and the fluoride anions have taken up all of the tetrahedral holes. Because each atom in the FCC array has two tetrahedral holes, the stoichiometry of the compounds requires that both of the tetrahedral holes can be occupied for each the cationic FCC sites. Cations tetrahedrally coordinate anions, and cations are surrounded by 8 tetrahedral sites, all of which are occupied, making the cations 8 coordinate. As a result, the fluoride structure exhibits 8 for coordination. The last crystal structure is ABX3 crystal structure. A and B are two ions of varying size, and X is an ion, usually oxide, that bonds to both of them. The A atoms are larger than the B atoms in general. The B cation is in 6-fold coordination surrounded by an octahedron of anions, and the A cation is in 12-fold cubo-octahedral coordination in the ideal cubic structure. Additional perovskite forms may exist in which the A and B sides are configured as A1x, 1A2x and B1y, 1B2y respectively, and the x deviates from the ideal coordination arrangements as the oxidation states of the ions within the A and B sides are varying. The second structure of ceramic is glass structure. Their short-range structure, particularly at high temperatures, often resembles that of equivalent crystalline compounds. Cations with low coordination numbers 3 or 4 are surrounded by bridge anions, each linking two coordination polyhedra at corners rather than edge in single component glass forming system. The low thermal expansion coefficient TEC, high viscosity at low temperature, and high melting point of SiO2 are all defined by a matrix of SiO4 tetrahedra. ZeO2, BeF2, B2O3, and As2O3 are examples of single component glass forming system.
Assalamualaikum. My name is Nurul Iman. I'm a metric 1202534. I will explain about one of the components in the ceramic, which is silicates. So what is silicate? Silicate is one of the minerals that we can find in earth. The majority of minerals that make up the rock of earth crust is silicates. The basic unit for all silicate is SiO4 minus tetrahedral. Like the structure of silicates, you guys can see on the slide, we can combine SiO4 minus tetrahedral with other SiO4 minus by having them share corner, edges, or faces. For example, two SiO4 minus tetrahedron will share an oxygen atom to form Si2O76 minus or forsterite. As we can see, the SiO4 minus is an anion, so they need a cation such as Ca2+, Mg2+, and Al3+, to act as a neutralizer and provide ionic bonding to them. Next is layered silicates, or we can also call as clay silicates. The structure of layered silicate consists of SiO4 tetrahedral connected together to form a 2D plane. It consists of particles that contains anionic layered silicates and metal cation. Silicates need cation to balance the charge. For example of layered silicate is Si2O5 2-. There are three examples of layered silicate, which is kaolinite, micas, and bentonite. First is kaolinite or kaolinite clay. Kaolinite clay will alternate layer with Al2OH42 plus layer, and each kaolinite layer will has one silica tetrahedral sheet and one aluminium octahedral sheet, and this sheet will loosely bound by van der Waals forces. Next is micas. Micas is a silicates minerals known as sheet silicates because they form in a distinct layers. And the properties of micas is resistant to heat and they not can conduct electricity. The third one is bentonite. Bentonite formed by the alteration of volcanic ash and rocks after intense contact with water. Bentonite can increase its volume several times when coming into contact with water. And the application of bentonite is used in molding sand, drilling mud, pelletizing, and absorbent. Bentonite can be used as absorbent as it have high specific surface and it gives large capacity for both absorption and adsorption. Now we will see about the structure of carbon forms. Carbon is also one of the material in ceramics. We will see 4 types of carbon, which is diamonds, carbon black, graphite, and fullerenes. And actually we had learned about this type of carbon from last semester, which is in the topic of carbon allotropes. What is carbon allotropes? Carbon allotropes is an element that can exist in more than one physical form. So the first type of carbon form is carbon black. Carbon black is a divided form of amorphous carbon. It has a surface area of 1000 meters square per gram, and carbon black is used to strengthen rubber in tires, act as UV stabilizer, pigment, and conductive or insulative agent in rubber, plastic, and coating. Next is diamond. Diamond is a tetrahedral carbon. It is a giant covalent structure, which means that giant covalent structure contains many atoms, and each atoms will join to the adjacent atom by covalent bonds. This means that this structure is extremely strong structure, and each carbon will share electron with 4 other carbon atoms. The properties of diamond is, first, diamond is hard. This is due to very strong covalent bonds operating in 3 dimensions. Second, diamond have a very high melting point, and third, diamond is not conduct electricity. The application of diamond is useful for cutting tools, drilling, and grindings, as we can see that diamond is a hard structure. Diamond can also be used in jewelry and also semiconductor in industry. The third type of carbon is graphite. Graphite is arranged in layers that slide over each other. Graphite have an aromatic layers. Graphite also is the only non-metal that can conduct electricity. Graphite have a weak van der Waals forces between the layer, and the structure of graphite is the plane can slide easily, and this makes graphite a good lubricant. The application of graphites in our everyday life is to be used as a dry lubricant, to make a pencil, and to make an electrode. So in this slide, we can see more detail about the structure of graphite. So let's see the figures. First, each carbon atom in graphite is joined with only 3 other carbon atoms. Next, the bond that exists between the carbon atom is a strong bond. And we can see that the forces that hold the layers of carbons together is a weak forces, which is a van der Waals forces. The last one is fullerenes and nanotubes. Fullerenes is prepared by wrap the graphite sheet by curving into ball or tube. They are spheroidal, having the composition of C to N, where N is equal to or bigger than 30. One of the examples of fullerene is Buckminster fullerenes, or C60, or we can also call as buck balls. Other examples of fullerenes such as C70 and many others. We also have carbon nanotubes. Carbon nanotubes are cylindrical carbon molecules, and carbon nanotubes exhibit extraordinary strength, electrical properties, and is an efficient heat conductor. As we can see in the picture on the right slide, the ball-like shape is a Buckminster fullerenes, and the cylindrical shape is the carbon nanotubes.
Hi everyone, my name is Shifa. My matrix number is 1202557, and I'm going to talk about the processing of ceramics. So for today, I'm going to show you videos on each of the process so we can understand it better. So first, I'm going to talk about how we prepare the raw materials. So first, we are going to crush and grind the ceramics to make a ceramics powder. So there are 3 steps on how to do it: ball milling, roller milling, and lastly impact grinding. So I'm going to show each one of the steps, each one of the ways of the process, of the video process. Okay.
In this video, we will talk about the working principle of ball mill machine. The ball mill is mainly composed of a cylindrical barrel, a feeder, a drive bus, the large ring beer, and a motor. The grinding operation is carried out in the barrel of the ball mill. After the grinding medium in the rotating barrel is brought to a certain height, the medium will fall due to its own weight, and the ore contained in the barrel will be subject to the violent impact of the medium. On the other hand, the grinding medium revolutes and rotates along the axis, and the crushing and peeling forces on the ore will be generated between the grinding medium and its contact area with the barrel, thereby grinding the ore. The ball mill steel ball is lifted and raised to a certain height when the cylinder rotates. Due to the gravity of the steel ball, it finally falls along a certain track. The steel ball in this area is subject to two kinds of forces. One is the force supplied to the steel ball from the tangential direction when rotating. The other is the force that is symmetric to the diameter of the steel ball and is opposite to the above force. The above two kinds of forces will form a pair of force couples for the steel balls. Since the steel balls are squeezed between the cylinder and the adjacent steel balls, the force couple will cause friction forces of different sizes between the steel balls. When the ball makes a revolution with the axis of the cylinder, it is thrown from top to bottom in the area, and it has a strong impact on the ore of the cylinder in the area, breaking the ore. It can be said that the ore in the mill barrel is mainly ground by the action of abrasion and peeling force, impact force, and squeeze force. Have you understood the working principle of ball mill? If you have any questions, please subscribe our channel. We'll publish more videos about ball mill.
Next, the clay composition for ceramics is 50% of clay and filler, which we use quartz that is finely ground for 25%, and lastly fluxing agent. Usually we use feldspar. The purpose of fluxing agent is to bind the materials together, and we use it for 25%. Lastly, it is powder processing. The purpose of powder processing is to convert the ceramics to useful shapes. So there are three ways to convert it. First is slip casting, second is tip casting, and lastly injection molding.
Slip casting is the first step in a long process that the mixed clay, which comes from Wales, Cornwall and Staffordshire, will undergo before it reaches your kitchen table in the form of your favourite polka dot mug or Union Jack teapot. The slip casting process starts early in the morning when the team of 12 men will arrive between 5:30 and 6 o'clock to fill their moulds with liquid clay, or slip, which has the pouring consistency of carnation milk or double cream, depending on your taste. Liquid clay is poured into the moulds, which absorb the moisture from the slip. Each of the moulds are left to set to a certain thickness, depending on which pattern they are. A small piece, like an egg cup, will take about 27 minutes to reach its set thickness. A Dove tea light holder will take less than this, closer to 15 minutes, and a mug will take 40 minutes. The bigger shapes take longer. A teapot will take about 50 minutes and a jug about an hour. This timing is important and precise. Leave a mould too long and you'll end up with a heavier, less elegant mug, which will have to be discarded, the clay reused for another casting. But if the moulds are tipped out too early, the cast will be too thin, so skipping off work early on a Friday afternoon is a bad idea. When the moulds are ready, the wet clay is tipped out, leaving a cast of each shape. The shape is then smoothed on the inside, sponged and finished off, then removed from the mould and set onto shelves to dry. It now has the consistency of an Easter egg left to warm slightly too long in the sun. To stop the shape distorting as it dries, a ring is put around the rim, forcing the piece to hold its shape. Each piece is left to dry overnight or for at least 12 hours. Every mould is cast twice in a day, and about 3,700 pieces are cast daily, depending on what sort of pieces are produced in that day. A run of teapots will take longer than a run of egg cups, of course.
The molding process of industrial ceramic injection molding is obtained by adding adhesive mixture to the powder, injecting it into the injection molding machine, and injecting it into the mold at a high speed at a certain temperature and pressure.